Okay, so our first topic for this lecture, or part 2 of this lecture, is spherical lenses. So in spherical lenses, these are cross sections of some simple spherical lenses where each surface of the lens forms part of a sphere, and the sphere may have radius greater than 0 according to the sign convention, which means it's a convex spherical surface, and that is a radius curvature greater than 0. This is a concave spherical surface, which is lesser than 0, and therefore the R1 greater than 0, R2 lesser than 0. That's called a biconvex lens, which I know is a little bit confusing. But the other important lenses to note here are the planar convex, where one of the surfaces is infinity, which means it's a plane surface, and the other one is again a concave surface, which is R2 lesser than 0. In the same way, the biconcave lens, you first encounter a concave lens, a concave surface, so R1 lesser than 0, and then the other one, R2, is greater than 0. And similarly, for the planar concave, one of the surfaces is infinite, the first one, and the second one is greater than 0. Okay, so that brings me to the derivation of the thin lens equation, which I'm going to do for a spherical convex biconvex lens. And so as you can see here, I've drawn two spheres. The first one, which is centered at the point C1, has a radius R1, and that is the first surface encountered by the rays, and it has a vertex at V1. Similarly, there's a second surface whose radius of curvature, as we just discussed, lies to the left of the vertex. Therefore, its radius of curvature is negative according to the sign convention, and that radius is R2. And we have taken that the rays which start from the point S are lying in the medium NM, and they exit also into a medium of refractive index N sub M, while the lens itself has a refractive index N sub L. So to draw the rays, let's look at one of the rays which come out from the point S over here, okay? And this is a situation where we have a real object, so the rays are appearing to diverge from or emanate from that point S as part of a spherical wavefront, and therefore these rays are all going to emanate sort of radially outward like that. Oops, for some reason wanted to do that. And so those two rays emanate, and then they're going to undergo refraction. Okay, so when they emanate from this, when they hit the second surface over here, these rays appear to be coming because of their refraction, appear to be coming from a point over here, which I'm drawing these dashed lines. So therefore, this is what we would call a virtual object, that is, this is an image which is not being actually formed like we were discussing, but this is an image that is serving as the object for the second point over there, okay? And so the P prime, which is at a distance, which I've drawn as SI1 over here, serves as an object for the second surface, R2, which is having a vertex at V2, and the object space for the second interface, that is the refractive index for the second surface, which contains the point P prime, has the index N sub L and not N sub M. Even though P prime appears to be in the medium of refractive index NM, what matters is that the rays that it is emanating are traversing a medium whose refractive index is N sub L. And so this will explain in a minute why I write the equations that I do. So the first surface, the index, just simply follows the basic spherical surface equation that we have already seen in the last lectures, which is that the first object point SO1 has the associated refractive index NM. The second object, the image, has the refractive index N sub L. Therefore, NL divided by SI1 is equal to NL minus NM divided by R1. And this is just the equation for a refraction at a spherical surface. Okay, and now we have to ask ourselves, what is the equation that we need to write for the second surface? Well, for the second surface, we want to write down the object distance, and the object distance is going to be measured from the vertex V2. Okay, and to measure that distance, I'll extend these lines down here. This is the distance, right? And that distance is SO2. Okay, and you can see it differs by the thickness of this lens over here, which is D. Okay, so SO2 is simply SI1 plus D. Okay, the magnitude of SO2 is equal to the magnitude of SI1, I'm sorry, plus D. Okay, and SO2 is to the left of the point V1, so SO2 is positive. That is, SO2 is simply equal to its magnitude. Okay, and SI1 is also to the left of V1, so SI1 is negative by the sign convention. Okay, therefore SI1 must be written as minus of its magnitude, SI1. And therefore, if I were to substitute now, SO2, which is equal to its magnitude, is equal to minus SI1 plus D. Okay, I hope that's clear. Okay, because SI1, when it comes out of this equation over here, the first equation, which I wrote over here, when we solve for SI1, SI1 will come out negative because it arises to the left of V1. And therefore, to correctly get the object distance SO2, I must take the negative of that SI1 and add it to D. And as you can see, that will give us exactly SO2 by this construction over here. Okay, so now we can do the second surface. Again, I will point out to you that because the rays that traverse the medium NL over here are emanating from the object point P prime, and these rays, therefore, it's as if this entire sphere to the left of it was filled with the surface with a material of refractive index N sub L. And now we can substitute for SO2 by that construction that I just showed you as minus SI1 plus D plus NM divided by SI2. And therefore, and that of course, we now put in NM minus NL divided by R2. And this is equation 2. And let's assume that NL minus NM is greater than 0. And since R2 is lesser than 0, because C2, remember I told you at the very beginning, C2 is to the left of the vertex V2. So the RHS of this expression on the RHS of equation 2 is positive. Okay, and so we can add equation 1 and 2. And so again, to remind you, there's equation 1, here's equation 2, and we get that NM divided by SO1 plus NM divided by SI2 is equal, let's make those subscripts a bit more clear, is equal to NL minus NM times 1 over R1 minus 1 over R2 plus NL sub times D divided by SI1 minus D times SI1. Okay. So if D goes to 0, which is what the thin lens equation is, if D tends to 0 in the limit of a thin lens, then we can get 1 over SO1 plus 1 over SI2. Sorry, once again, my subscripts start to get bad here on this writing. 1 over SO1 plus 1 over SI2 is equal to, now remember we have neglected that last term, which is this one, we've set it to 0. And that gives us NL minus NM divided by NM times 1 divided by R1 minus R2. And notice that in the thin lens limit, if D becomes very small or negligible, then V1 and V2 coincide, which means that SO1 we can just replace by SO, and SI2, by the way, SI2 I didn't draw it over here, but hopefully it's clear. This is SI2. You can see that SI2 and since V1 and V2 coincide, there's no point in distinguishing between surface 1 and 2 anymore. So we can simply replace this by 1 over SO, object distance, plus 1 over SI, image distance, is equal to, now I'm going to assume, for example, that typically if the lens is sitting in air, then this is just NL minus 1 times 1 over R1 minus R2. This equation is called the Lensmaker's equation or Lensmaker's formula. And further, for in the limit, if say SO goes to infinity, right, just like we did for the spherical surface, then we know that the limit of SO going to infinity, when we solve for SI, we call that the image focal length, right? Image focal length. And similarly, limit SI going to infinity of SO, we call that the object focal length. But in the limit that from this above equation, we can see that in either case, when one of these two goes to infinity, FO and FI are going to be equal, and we call that the focal length is just equal to something called the focal length, which from this above equation is simply NL, so that's called the focal length. And from this above equation, we're going to equate that to 1 over F. So 1 over F. Remember, whenever we do this, when we equate this to 1, if I set this guy to 0, that is 1 over SI to 0, which means SI goes to say infinity, then 1 over SO equals some quantity, and I'm going to call that quantity on the right-hand side, which is this guy, as 1 over F. So, and 1 over F, therefore, from this expression is NL minus 1 times 1 over R1 minus 1 over R2. Okay, so this is very important. This is the governing equation for a lens given its index and its radii of curvature. And this tells us that this is the focal length of that particular lens. And from this, 1 over SO plus 1 over SI equals 1 over F for a thin lens. And this is called the Gaussian lens formula. Okay, which is just basically taking the Lensmaker's formula and realizing that for a thin lens, there is only one focal length F on either side of the lens. So that 1 over F is NL minus 1 times 1 over R1 minus 1 over R2. And therefore, this equation can be used to produce our expressions for the object and the image focal length, object and image distances just from that expression. And so we can use this once we are given a focal length for a thin lens, we can simply use it in this equation to find the object and image distances.